actions, submanifolds, and perhaps by time, the connection between that and singularity, since that's another one of the three. When I invited several topology friends, and each had the same reaction, what a delight it would be to go back and look at the wonderful book of Santiago. Beautiful again, because it has this terrific integration of general ideas and working out of and but to me, the most wonderful thing about the book, which I hope you'll get in the course of my lecture, is the way it had all kinds of little puzzles and time went on. So I'd like to give you some of those examples. Perhaps I'll discuss some seeming paradoxes that came out of the book and their resolution over time also, and how that went. So the book is so inspirational that Santiago, López, the Medrano, Santiago, 5 great Mexican nations. To begin with, of course, is it's the observation of many great 20th century mathematicians and physicists that symmetry plays an unexpectedly large role, in particular geometric symmetry, mathematics and physics. When I was studying the symmetry of an object, in particular studying the geometry of, say, a manifold or a space, much more information about the nature of a priori imagine, and lead to all kinds of directions that have first to do with questions about symmetry. It's one of the great mysteries of nature that guides when we look at the vast world of manifolds. Symmetry seems somehow one guiding light that we have as we go through it. Now, in the context of topology, deep results on symmetry began with works on the homology points. Smith. And already in the work of P.A. Smith, what one was trying to do was use standard models that one had given to you by nature, very elementary, say, for example, the linear examples obtained by linear group actions in space on spheres by linear representations. And then the program would be to try and see to what extent those models general actions. And the early results were along the lines of trying to prove that group actions more generally, that symmetries of spaces more generally, behave in some homological or homotopical way similar to those that given from the known examples in that we could try and say something about the homotopy or homology, starting, as I say, with the work of P.A. Smith. And that's an important, very important direction in mathematical thinking and topological thinking, which continues actively to the present moment. There are several people here who have contributed to that line of development. But early on, as soon as people began to be able to say something about the classification of manifolds, to that to the 50s, to be an interest, could one do more than just say something about the homology and homotopy of symmetry, to try and pin down some results about actual classification of symmetries? Could one say in natural context? Could one say something about what a set of all symmetries look like, say on a sphere, which is the most natural manifold to start off with? And one of the signal accomplishments and of his early efforts was that he presented the first success of this program in the classification of involutions on spheres to begin with, and of course more generally in studies of involutions on manifolds. But on spheres, this was a remarkable success quite early on, which gave us information, which gave us a total picture of to what extent group actions in some natural setting resemble the linear situation. So, of course, if we're looking at a sphere, Sn, then our acts on this, and this acts on this by the usual involution. And it's not hard to prove that if you have any fixed point free involution, like the usual involution that sends a point to its vector to its negative, if you take any fixed point free involution on a sphere, it's not hard to prove that the quotient space divided by this looks like the quotient of the standard involution. The standard involution is the atypical map, and if you take the standard involution and divide by that, it's called an alpha, then of course what you get is RPN. So this should not be equal here. This is homotopy equivalent to this, which is RPN. So that from a homotopy theory point of view, as soon as you're in a very restricted context, okay, great colors. Thank you. Thank you. Okay. So you can actually take a try and in particular, you're committed towards studying connected manifolds if you're going to study group actions, because the quotients, in this case, for example, have a fundamental group, not trivial fundamental group. Here, the fundamental group is Z2. The fundamental group is Z2, so I wanted this. So if you're going to study general evolutions, you're going to study manifolds that are homotopy equal to RPN, and in fact, one can show then that the classification of involution, the classification of fixed point free involutions is really in fact the same as the classification of manifolds homotopy equivalent, manifolds homotopy equivalent to RPN. And in fact, Santiago's success in classification of such manifolds was the first significant success in the world of compact finite group actions in getting such a complete classification story going. Now, what I'd like to do is say something. I'm going to generally, since this is sort of meant to be a survey talk, I'm not going to try and say, I'll try and keep everything I say correct, but I'll not try and say technical details here. I'm going to just try and get a general picture of what the progress of the subject has been like. So, let's say, first of all, what kind of ingredients went into the soup of classifying these spaces? What is it that I've used to classify homotopy manifolds, homotopy equal to RPN? I guess, by the way, when you first see it, it's of course a surprise that there even are such creatures, that there are manifolds that resemble RPN so closely and yet turn out not to be homeomorphic to it. And by the way, I'm not being so careful here about discussing smooth PL or topological, but when I try to say things that are more precise, they'll usually be PL or topological over here. I'll try and say something about the smooth case as well. The question exists in all settings, so it's a natural question in all those settings. Classification of manifolds, it's clear that there are certain things you expect to see. Well, if you're going to classify manifolds, how are you going to do that? Well, one thing you could try and do with distinct manifolds, of course, is you could use their homotopy type. That includes the homological information. But that's already subsumed in this discussion because the study of fixed point free evolutions turns out to be the same as these over here. By the way, I didn't say, but of course, the way you go back from a manifold homotopy equivalent to RPN to a fixed point free evolution is, of course, by taking the universal cover and then looking at the covering translation over there. That's how you go backwards. So what kind of ingredients could you imagine would go into this? Well, if you're thinking about classification of manifolds, we've already gone beyond the stage of the homotopy type, what more could you say? Well, the next thing you could hope for, of course, is information about the tangential geometry, about the tangent bundle, which gives you information about the infinitesimal geometry of space, and moreover, it gives it to you in a form which you can hope to study by the methods of algebraic topology again, so that even though you're studying an invariant that's more refined than homotopy invariant, algebraic topology, the homotopy So naturally, if you're looking not just at RPN, but any manifold, you would think beyond the homotopy type, you might think of the next variant that you would look at would be information about the tangent bundle. And that contains a lot of information about a space. And that's usually unwound in various ways. One way that the tangent bundle is unwound is that the tangent bundle the vector bundle of decay theory, it's often more convenient to take that information and for computational purposes turn it into homological or cohomological information. And that's often done explicitly by theories of characteristic classes. So if you apply some theory of characteristic classes, then what that does is it gives you associated the vector bundle or the tangent bundle, it gives you gadgets that measure the tangent bundle, the tangent bundle. So these are going to be, or any bundle for that matter, and these will take values for appropriate coefficients. So naturally, the next variable you think about using is, say, the characteristic classes or some refinements of them to study the tangent bundle. And that's obviously the next level down thing to use. And that's a big part of the general story of manifold classification. In fact, that's a big ingredient in the story. But one needs to go further than that. There are various ways to refine this. An important way of refining this is the following observation, which is that, and here I'm summing up lots of people's efforts that gave us this insight, which is that when you study tangent bundles, manifold homotopy equivalent to RPN, if you study some manifold that's homotopy equivalent to RPN, you could of course compare the tangent bundle space and compare it with the tangent bundle of the target space, say in the present instance RPN. When you compare these tangent bundles, they're not quite arbitrary in their relationship. They, of course, if these manifolds were the same, these bundles would be the same. But even if the manifolds are just homotopy equivalent, there is a very weak sense in which they're related. They're not the same, but there's a weak sense in which they're related. Namely, they're related as homotopy widgets. Being related as homotopy widgets means that they're associated. These have the same equivalent. I'll just say same for short, to be less precise. Oh, okay, thank you. Yes, is this okay? Do you want me to switch to this? The advantage of that is that I can face you, but this seems to be working all right for the moment, okay? No, I think we'll continue as is. Is this okay, or will you prefer we switch? I'm indifferent. It's okay. What? You're indifferent. I'm indifferent too. What? Keep going? Okay, thank you very much. Leon and his wife have been taking care of me from the moment I arrived here, so. These have the same associated spherical fiber space. Which in a technical way means that the tangent bundle over here, thought of, for example, as a linear bundle, let's say is a map to the classified space, BO, becomes the same when you think of it as a map to the classified space with spherical fiber spaces, which is often written BG or BF, like that. So this is a weak sense. This is a much smaller space than this one. But anyway, there's a weak sense in which when you have homotopy equivalent manifolds, the bundles already are somewhat equivalent. Now you can take advantage of that equivalence in order to refine the characteristic classes slightly. So that instead of just defining the characteristic classes, instead of thinking of the tangent bundle as a map from here to here, because the tangent bundle, or more precisely the difference of tangent bundles, is trivial over here, you can actually lift this map to a slightly more refined space, in this case called G over O. And this is what's called in topology, in manifold theory, a normal invariant. It's normal invariant where that comes from the fact that one usually does this in terms of normal bundles rather than tangent bundles, but it hardly matters. And I've just discussed it geometrically in terms of tangent bundles. So this is a slight refinement of the tangent bundle, and you should think of it as a very slight refinement because it turns out that this space is rationally, for example, in terms of its homotopy groups or homology groups, this space is actually not there. So this is irrelevant rationally, and therefore from the point of view, say, of rational haven't really gained anything. And so most of the time, this is a slight refinement. So you should just think of this as still capturing the tangent model, but with some extra technical refinement thrown in. And still measurable by characteristic classes. Fine characteristic classes than the obvious ones, but much in the same flavor. Much in the same spirit. Okay, so the upshot is that that's the first set of invariants one would expect to see. And indeed, it had already been shown as a result of Browder-Novikov surgery theory and its reformulation by Sullivan, it had already been shown that this story that I've just told you is already enough for simply connected manifolds to give you a lot of classification theory in high dimensions. So that the homotopy tied together with this kind of data already pinned down the classification of manifolds, actually. That corresponds to Crevert-Milner had first done the classification of the spheres, and then Browder-Novikov had done it for general simply connected manifolds. And so this information roughly sums up what that story is like. Now, however, when we go with the non-simply connected manifolds, it was pretty clear from early on that there would be a more complex story, and a very interesting story because it began to involve the fundamental group, which contains a lot of the most interesting information in topology often, and issues about the fundamental group. So the question was, what happens further when one is thinking about the role of the fundamental group and how does it interact with these other invariants like the characteristic classes and so on. This is a complicated story which I'll try and tell you a little bit about. It's not a story which is even to this day completely answered because, for example, the Novikov conjecture and the Borel conjecture and several other intertwined conjectures which are central in topology turn out to be reformulatable in terms of the question of interaction between the fundamental group and the characteristic classes. And those conjectures are not, even though there are many, many interesting and important cases which have been worked out, those conjectures are not entirely known to this very moment. And so there's a story here that is not only going to the present, but is going on as we speak. But let me say a little bit about what happens for the fundamental group Z2. One of the things that, so let's specialize a little bit in the fundamental group Z2. And for fundamental group Z2, I'm going to summarize crudely one of Santiago's principal results, which is that the classification of these involutions, or the classification of these homotopy RPNs, these fake RPNs as they're sometimes called, could be done by two invariants. One invariant, and we've already, of course, the homotopy type is subsumed when I said homotopy RPNs, so that's built in. One invariant we just said is kind of these tangential invariants. So I'll just say refined tangential invariants, the kind that I've been discussing. And these, by the way, because the homology of RPN is entirely to prime 2, these are in this case these all involve order powers of 2. There's no elements of infinite order here. Worse, you see Z4 is actually the calculation that actually comes up. But that's not the whole story because, as we said a minute ago, there is the role of the fundamental group as well, and now it turns out to contribute to the picture as well. Now, there are various ways to think about the contribution of fundamental groups. And I'll try and give a brief outline in the non-technical terms in a moment. There is a theory which starts in the simple connected case with Browder-Novikov work and its reformulation by Sullivan, and then its enlargement to the non-simple connected case by Wall. There is a theory called surgery theory, which gives one a language in which to discuss this kind of problem in general about the role of the fundamental group. But the general formalism of the theory, while wonderful, doesn't tell you how to actually compute any particular example. And if you're actually going to do examples, you need to have some hold on the fundamental group or some way to actually get hold of concrete invariants as opposed to just having a general framework. And early on, of course, what we knew mostly about was simply connected manifolds. So naturally, it was a hope, particularly encouraged by Bill Browder, that one could try and go quite a distance by trying to, for example, take things and break them up in some way into simply connected manifolds, or take advantage of methods that somehow had a simply connected flavor to them. And in the process of doing this, Browder and Lipsey developed something called the Browder-Lipsey invariant, which I want to discuss for a second. The Browder-Lipsey invariant, by the way, I forgot to ask how long this talk is supposed to be. 1 hour. What? 1 hour. Sorry? Keep going? idea of the Browder-Lipstein variant was very simple in its essence. You see, if I have an involution, the natural way to get another involution in the next dimension, well, in fact, in general, in topology, the natural way to raise the dimension of an object is to take its suspension. And so there's actually an analogous construction in the language of involutions. Namely, if I have an involution on a sphere, if I had an involution on a sphere, so here's supposed to be some high-dimensional sphere which has a Z2 action, then of course I can construct the next higher-dimensional sphere by taking two cones, one on the bottom and one on the top, two hemispheres, two cones on the sphere. So here's a sphere, say Sn. And now I can extend the involution from what is now the equator to the rest by just flipping the two sides, in addition, flipping the top and the bottom. So that's called a suspended action, and that would give me an action, so we get a Z2 action on Sn plus 1 this way. And as you see, this is the suspension equivariant of the original action like that. And the Browder-Lipstein variant was an attempt to go backwards and to try and see, well, this is such a natural construction, and obviously built into the world of symmetry, of course, you should try and see, can you always go backwards? Can I take an involution on a sphere, and can I desuspend it? So this is the obstruction term. This is the obstruction to desuspension. This is the obstruction to desuspension. And I'll tell you in a word what the obstruction to desuspension looked like without writing down any technical details. The idea was the following. You looked at some homotopy sphere, in this case I'm labeled a dimension with an action, say of dimension n plus 1, and it's not difficult to construct some submanifold here. And in a natural way, some manifold which sits in this as an equator, actually here. And then the idea would be, well, if you want to make this a suspension, you have to somehow improve this submanifold to get rid of its homology so that it looks like a sphere. So you need to do what's called ambient surgery, which is modification of the submanifold, but modification within the bigger manifold that's over here, like that. And the Browder-Lipstein obstruction was the obstruction to ambient surgery. But more, what it really did is the following. It turned out that the way you study the abscess was by looking at homology classes in the middle here, and you had to worry about how the homology classes were sitting in here in the middle dimension in terms of how they intersected their translates. So you had to compare classes, class here and its translates, so let me write G of the class. And you had to study, for example, the way in which classes and their translates intersected. Now, usually when you did surgery theory, you ended up studying the way classes intersected other classes, including themselves. But here in this equivariant situation, it was now the way classes intersected their translates, because that carried the equivariant information. If you did that, you would get an invariant which was amazingly similar to what you got in the simply connected case, because in a way you peeled away the fundamental group. See, the fundamental group had two elements in it, E and the non-trivial element G. But now you're paying attention only to the way classes intersect one of those, just G of that. So in a way, you'd like cut down the fundamental group by 2, and in fact, you're ending up with a situation which has formally invariants that are very similar to the simply connected case. So you get out of this an appropriate dimension, for example, signature invariants, and things like covariant invariants and so on, signatures, etc., as in the simply connected case, come up. They come up, of course, with some little changes. One change is that they're coming up with a shift in dimension, because over here you start off with an n plus 1 dimensional manifold, but you're actually doing your work in an n-dimensional manifold, so the parity is switched from even to odd. They also come up with a shift in orientation, because the flip here involves orientation, and so you have to keep track of that. So there are various technical modifications of what happens, but those only turn out to provide shifts of the way the simply connected invariants are coming up. And so in the end, these were invariants that are very similar in a formal sense, with a shift in dimension and orientation compared to the usual invariants. So that meant that these were kind of understandable, though one didn't know much about their realization and about when they came up and so on. And Santiago's theorem is that, in fact, the classification of homotopy RPNs, one of his theorems, one of his basic theorems, could be completely written down in terms of these defined invariants and these Browder-Lipstein invariants. These were either 0, Z, well, just like simply connected search instructions, in some dimensions they were Z2, in some 0, in some Z. In the Z case, it's a signature, and then there's another dimension where 0 depends upon the dimension mod 4. And I focused on the Z case because the signature is the easiest of the ones to understand, and a trivial one to understand. And then the theorem was that that's the whole story like that, and you can find that theorem in his book. So this is a very beautiful picture that gave one a complete understanding of what, in fact, evolution constitutes look like in higher dimensions. Santiago did this originally in the PL case, but by the time he had finished doing it, the machinery existed doing Kirby and Sylvain for translating this into the topological case. In some cases, in many cases, that gives even simpler answers. And so he got a very similar story in the topological case as well. In the smooth case, the story is a little bit more complicated. And Santiago has a lot of interesting special results on the smooth case. But there isn't as clearly a systematic picture of what happens in the smooth case. I believe that it's within the capability of present-day homotopy theory to actually complete the story in the smooth case as well. By now, we know enough about the relevant classifying spaces that it should be possible to give a complete classification of smooth involutions on spheres. Let me make a parenthetical remark that, in general, the classification of manifolds in the topological PL case turns out to have a group structure. That's not always true in the smooth case. There are examples where one can show from non-simply connected cases, there are examples where one can show that there is no natural group structure on the set of smooth manifolds in a given homotopy type. Weinberger has an example to show that. Okay, so I don't know if that's true for RPNs, though. Might well have a group structure in such a simple case, probably does. Okay, so in this way we got a complete Santiago got this complete classification. Now I want to carry this, there's more in Santiago's book and in his early papers about, there are other themes that I want to carry forward besides the theme of classification. But let me continue with the theme of classification and try and move forward a little bit just on that from there to the present. And the truth is I'm going to have to omit tons of interesting, I mean, you know, when you try and take a classical work and try and draw it to the present, you're doing violence to the history, first of all because you're omitting things, and naturally everything that you cite has many inspirations leading into it. So that's the nature of life. Any such story is by its nature a very, very partial account. You have to forgive me for that. And inevitably the story is tinctured by my own work and my own interest in Santiago's work in a way which has inspired often inspired my own efforts. Okay, so one had this picture let me say a few words about another technology that came into this, which I alluded to also, and which is going to come up more as I speak about what happens for more general groups. So, another way of approaching the general problem, or in fact, a general way of approaching the problem of classification of manifolds, and as we saw, classification of non-simply connected manifolds is intrinsic to the study of transformation groups. So, was summed up by an exact sequence, which, as I said, is Wald's exact sequence, which is based upon Sullivan's reformulation of the results of Browder and Novikov. And that was said this way. Let me speak approximately and say that, again, we're interested in the set of manifolds in a given homotopy type, so that's called the structure set of M, and that fits into an exact sequence. And the exact sequence has what other terms in it? Well, so this summarizes the classification of manifolds in a given homotopy type. And as we said, the first key ingredient that you pick up is the tangential information, the tangent bundle information, and that's summarized by something I already alluded to, namely to be described in terms of the difference of tangent bundles, which, if you refine it, as I mentioned, you can, is a map, for example, in a topological case to the space G over top. So this is a little bit more information of the tangent bundle. But you should think of this information as capturing a refined tangent bundle. And this can be computed using characteristic class methods, as we've already said. But that's not the whole story, because you can have two manifolds that have the same characteristic classes, and yet there's more information. As usual, in an exact sequence, you can continue it to the right and to the left. So I didn't leave myself room, but I would say if I continue this to the right, what's the next term? Well, the next term is already suggested by what happens in the simply connected case. Namely, in the simply connected case, when you have two manifolds that are homotopy equivalent, one of the things that happens, of course, is that the signature of the two manifolds, the index, which is a measure of the middle dimension homology and its intersection form and the number of positive and negative eigenvalues in the middle dimension homology, there's a signature associated to that, the same signatures that come up in a Tia singular theory, and there's a signature invariant. Now, in a simply connected case, you just get an integer as a signature. It's the number of positive minus the number of negative eigenvalues of the intersection form in the middle dimension. When you go with the non-simply connected case, you're going to have not just the mutual signature, but you're going to have to study not only the way homology classes intersect each other, but the way they intersect their translates as well. So you get a more complicated kind of signature, or multi-signature, for example, in many cases, which can be summarized as kind of a quadratic form again. You would think of it as positive and negative eigenvalues, but not just over the integers, but now involving the fundamental group, because you have all these translates. So you get a quadratic form theory, which is called Ln, depending on the ring, not just the integers, but now you have the group ring of the fundamental group coming in as well. So you get this kind of story of it. And now once you see three terms in an exact sequence, of course you expect it to continue, and I won't go into the explanation of why it continues, but it's just natural to expect that it does, and it does over here. And this turns out to depend upon this number mod 4. It depends on the mod 4 because, for example, when I talked about self-intersection, I was implicitly assuming there was a middle dimension, which is even dimensional, so I was assuming n was even, and then whether you get whether n is 0 or 2 mod 4 affects whether you get a symmetric plus or minus symmetric forms. And then in the odd case, there's some other theory involving homomorphisms of forms that comes in. So this is a pattern that's familiar in algebraic K-theory, where you get some kind of widgets coming in, roughly a group of widgets, and then you get in some other parallel dimensions, the homomorphism groups of those widgets, and that's sort of what comes in. So there's some kind of an exact sequence like this that actually computes this guy. The problem is that the exact sequence doesn't tell you anything about this term, which is kind of an algebraic K-theoretic term, and it doesn't tell you even less about the homomorphisms that actually come in. So it's not just throwing the exact sequence at somebody, it doesn't really tell you much in the way of calculations. However, it does apply to this situation, homotopy RPNs, and one of the things that, so for example, in this case, you'd be looking at the L theory, the quadratic form theory, over the ring Z of Z2. Now, Z of Z2 is not a terrible ring, and Z of Z2 is nearly the same as, that's the ring of the elements of the form A plus BT, where A and B are integers, and T squared is the identity. Well, this is very close to being like two copies of the integers. It's not quite two copies of the integers, but you can map it to two copies of the integers by sending T to 1 to the minus 1. And it's almost an isomorphism like that. So, not surprisingly, this quadratic form theory breaks up into a quadratic form theory of integers and another copy of quadratic form theory of integers, roughly. And one of the beautiful things that Santiago did was he saw how this exact sequence could be related to this other approach using desuspension invariants, because he saw exactly how the quadratic form theory that you're picking up over here is related to Brauer-Lipsy invariants. So he understood the way in which the surgery groups and the Brauer-Lipsy invariants are related, and he wrote down exact formulas that told you how those invariants were related, and it also gave you a way philosophically of understanding the relationship between the approach of trying to classify actions by desuspension and the approach of trying to classify actions by using this exact sequence. The whole picture came together and all the pieces fell together. So that's a very beautiful picture that gave us a very complete answer. Now, I'll say a few words about what goes on further as we go beyond this to higher dimensional examples or to other groups. Well, in fact, before I go on to other groups, let me add one little piece, and which Santiago was very interested in, among many other phenomena. He was very interested in low-dimensional phenomena, and he gave many interesting examples of explicit constructions of involutions of low dimensions. But there's still many, in fact, there's still out to this day, many questions left in low-dimensional topology about involutions. But let me mention right away something that added to Santiago's work in low dimensions, which is an example due to myself and Shamson a few years later, that there exists an exotic involution, an exotic, smooth, PL, doesn't matter, smooth, or PL, involution on a force field. Now, since we don't have general machinery for smooth or PL constructions by surgery, for example, we mentioned before, this had to be done by an explicit construction. It's a very pretty explicit construction. I don't think I'll have time to give it here. I'll just mention it. It's done by kind of taking, it's almost by taking the standard RP2, the standard tube around it, as if you were an RP4, and then sitting outside of RP2 and RP4, what you usually see is a disc bundle over the sphere, kind of like a filled-in Klein bottle over the circle, And instead of a Klein bottle, instead of a filled-in disc bundle, non-oriented disc bundle over the circle, you fill in with a non-oriented torus bundle over the circle. And that turns out to give you, oddly enough, an exotic RP4. I think the surprise there is that it turns out to have the right homotopy type because you're using a torus in place of the circle, in place of the disc. But it's one of the things that Santiago emphasized in a context which I'll be describing a little later in my talk, I hope, that one often gets exotic homotopy types and complements of things in projective spaces, and that doesn't hurt the fact that they assemble into the right homotopy type because of the role of the fundamental group in this, actually. So it's quite an interesting phenomenon. Okay, so there actually is, by the way, we actually gave a construction of an infinite number of examples corresponding to a family of matrices. Those are all exotic, but to this day, nobody knows if they are different from each other. This result came before the great progress in four manifolds over the last 25 years, and that progress hasn't resolved any of the questions, however, about these examples. So one doesn't know if the different examples, we know all the examples we constructed in this family are exotic, but are there just two or an infinite number? I mean, we don't know. One also doesn't know about, there are also questions about using this kind of construction to generate counterexamples to the four-dimensional smooth part rate conjecture, which is still open, and that would be an interesting topic for another talk, which I won't do now. Okay, now, more generally, people are interested in the question of actions, and here, of course, I'm going to get sketchy now as I head towards the present, because there's so many topics I could talk about. Let me talk about free actions on spheres, just a little bit of what's been accomplished in the year since. So one thing that's been accomplished is that, for example, is that in principle we know which groups act this way, which groups act. There are groups which are not cyclic, which act linearly even freely on spheres. There are groups of order PQ that act linearly on spheres and so on. And one wants to know in general which groups act freely on spheres, and this is a long story in its own right, culminating in work of Wilbur and Madsen. I'll just mention Wilbur and Madsen. So the question of which groups act. There are topological conditions on a group acting, then it turns out that there are also manifold theoretic restrictions on it. I won't go into the whole story. It's a long and wonderful story, both on the topological side and the geometrical side. But as I said, this is just a survey, and I can't really go into that. Let me say a little bit more about what happens for cyclic groups. For cyclic groups, one actually aspires to a complete classification. So if you go from Z, fixed point free cyclic groups acting on spheres. There's a series of wonderful results associated with the names of Brouwer, Petrie, and Wall, which culminated in a complete classification for odd groups, for groups of odd order, for cyclic groups of odd order. In this business of group actions, so there's often a difference in flavor between the odd and the even case for cyclic groups of odd order. So here we're trying to understand the relationship to think about lens spaces. For Z2, the standard example was projective space. Here the standard example is lens spaces. And similarly here we're classifying what are called fake lens spaces. Those are the quotients of the sphere by linear actions of odd groups of cyclic order. Those are, just think about rotations on the circle, for example. That's the simplest example. And the general length spaces are given by just adding up those rotations on circles of various, just a bunch of circles. Then you add them up, you get a big rotation on a big sphere by doing that. So, and then those are the models, and then the question is to what extent do three cyclic group actions of odd order generally resemble those? Let me mention here that, again, there are relationships. Let me just tell you what the invariants that turn out to matter are in this case. In this case, what happens is that there are two kinds of invariants that matter. The classification for these is the classification of the odd case is in terms of just two invariants. Two invariants. One invariant is randomized torsion, suitably defined. So randomized torsion is an invariant that's just beyond homotopy theory's range. What it measures is how twisted up the chain complex of the space is. If you take the chain complex of a space that doesn't have too much homology, there's a way of assigning a determinant that measures how twisted the boundary maps are, actually how non-trivial the boundary maps are. And the randomized torsion is just a combination of those. And so it's really should be thought of as kind of a determinant of the whole chain complex, associated with the chain complex. And of course, as the fundamental group grows, you have more complicated chain complexes because you're keeping track of the back transformations, the covering translations on it. And so that's one very classical family of invariants that's used. The other family of invariants is multi-signature. Now this has various names depending upon which way you approach it. Multi-signature, if you approach it the way I described earlier, by quadratic forms. It's also called eight invariants. If you approach it using eigenvalues of Laplacian, it's related to the eight invariant. It's really the same invariant. And there are various other ways this eight invariant in differential geometry. There are various other ways to phrase this invariant. And it turns out that the classification of the odd group is completely in terms of these two invariants. You might wonder, I advertised so heavily the role of the tangent bundle earlier in the discussion of RPN. What happened to the tangent bundle invariants in the characteristic classes? That was the most naive thing to think about. But it turns out that they are actually encoded, in this case, in the odd case, they encode in here. So these subsume, these happen, it's not obvious, there's a computation that needs to be done to check this. These subsume the tangential invariants. The tangential invariants turn out to be included in these, not at all an obvious fact, actually. There's also a slight relationship between these two invariants, which if you're given classification theory, you have to write down mod 2 relationship between those invariants in certain settings, and so on, which I'll admit. Okay, so that's wonderful thing. Let me mention one other aspect of this theorem, which is a theorem of Wall, which is that in particular, it follows by looking at the classification, which has a dimension-independent appearance over here, as you can see. Wall's result says that all of these desuspend, all desuspend, all of these desuspend. Now, of course, you have to interpret the word desuspension in the odd order context appropriately. You don't have a group action on cones the way you had before on a suspension by flipping the two sides, because the natural involution is not on 2 points. The 2 points that you get is natural Z2 involution. But of course, if you take a cyclic group of larger order, what you need to work on is a circle. You can rotate a circle around, and that takes the role of 2 points. So when people talk about desuspension for groups other than Z2, they're talking about desuspending a circle action. So in other words, writing your action is the join of a circle with what you had before, rather than joining 2 points with it, because that's what you have to mean. Anyway, it's a very beautiful theorem of Wall's that, in fact, there is a complete desuspension story in this. And just to finish the story of the sigma groups, let me mention a new result of myself and Ming Yan from Hong Kong and Shmuel Weinberger from Chicago, which is a classification of the remaining case is sigma groups with an even order of sigma Some of it is, of course, already included in the multi-signature, some isn't, but one has to compute out exactly how much of it is computed here. Technically, there's some subtleties that come in. I won't run through what all the subtleties are, but I'll just mention that there's a new obstruction to desuspension. In this case, there's a new desuspension obstruction that is kind of unexpected that comes in at twice the prime power. Exactly at twice the prime power it kicks in, and then it brings for the higher order groups also as well. Yeah, so now I could go on to talk about, yeah, maybe I should say, I mean, this story can go forward in many different directions. So, how much time do I have? How many? What? What?
A lot of time, 25 minutes.
What?
25.
At least 25.
Okay. Okay. So, well, another part of the story, which I won't have time to say too much about, but let me say a little bit, which is that this story of group actions, this classification of group actions, notice free group actions and others, in turn feeds into another development that took place over the last 20 years, which is the solution of the problem of non-linear similarity matrices. And I'm not going to have time to discuss this in any detail. The problem of the Rand's problem about non-linear similarity matrices. So this is the problem about giving two matrices. For example, say two orthogonal matrices. To simplify, you of course have a classical theory, linear algebra, that tells you when two matrices are similar when they're conjugated in the orthogonal group. It's natural to ask when are they conjugated in the group of homeomorphisms, either in the group of homeomorphisms of sphere or in the group of homeomorphisms of Euclidean space, however, whichever setting you want to think about it. And it was already known, that in many, many cases, going back to the Rand, that in many, many cases, topological conjugation already implied linear conjugation of matrices. But considerations that led very much out of the kind of things that Santiago was looking at ultimately led to a counterexample to the Rand's conjecture. So Shadison and I found a counterexample using some of the same technology that fed into, or generalizations of the same technology that, so here there are various special cases when it was true. Let me mention here Sullivan, odd case, the group for matrices of odd order, and also Reinhard Schultz. These were second, but these were quite standards on. Many other cases, some go back to the Rand, Kuiper, some cases. Anyway, but it turns out to be false in general. False for 4Kn, for matrices of period 4n when n is bigger than 1. And what comes in is kind of familiar from the, coming back to, Santiago had emphasized the importance of thinking about classifying actions by suspending and desuspending, and he actually had obtained classification theories for that. Well, if you do the same thing for, not for group Z2, but if you look at the group, say, Z4n, and you study whether or not a matrix, whether or not an involution, whether or not the Z4 action can desuspend, you'll then to an analog of the Dada-Lipsy groups over Z4n. And then you end up comparing, Santiago had taken advantage of the fact that the classification of RPN to be mapped into classification by taking the line bundle of RPN, like the Mobius band, you get the classification of the line bundle. And the line bundle can be closed off to essentially be the same as the classification of the next projective space, RPN plus 1. So, and this is really the suspension, again, that I discussed a few minutes ago, is taken of the line bundle. But if you do the same thing for lens spaces of what is Z4n, you do the same thing for the lens space with fundamental group Z4n. And that's the same as looking at matrices of period Z4n and And then you take these line bundles, associated line bundles. Well, that isn't the lens space anymore because Z4n doesn't act freely on the cone, as I said before. But what this is like taking a matrix and stabilizing it by, taking a matrix and as an action stabilizing it by adding on a matrix A. And now the non-trivial line bundle is a kind of stabilization by an eigenvalue minus 1, corresponding to the fact that we flip as you go around. And then it turns out that there's a difference between the classification of these guys when you go to 4n. And we took advantage of that difference in constructing examples of matrices which were topologically, which were linearly of examples of matrices which when you went to here turned out to be topologically the same. And so by going further in this direction, we obtain examples of nonlinear similarity occurring in the natural world. So that's an interesting launch development, which I don't have time to go into. There's some recent work of Hamilton and Pedersen completing classification of matrices, topological classification of matrices. There are many interesting developments on the topological classification of representations, which I won't have time to go into in the present survey. Let me mention one other direction of work that is related to this. I've already emphasized that understanding geometrically the multi-signature was at the heart of some of Santiago's efforts. So, multi-signature. So let me say a few words about the multi-signature and its generalizations as to other groups. This is generalization means to general groups, to general compact groups. Say that's one generalization one wants. One also wants a generalization to topological manifolds in general, and one also, in fact, wants a generalization beyond manifolds to variety. Beyond manifolds to singular varieties. And if I go down this direction far enough, it will take me to your other topic of this conference, but I don't think I have time to develop this in detail. But let me just say that the multi-signature in its, and there's a story here, there's a generalization to topological manifolds, well, of course, the general groups, this is something included reading the Atiyah-Singer theorem, Atiyah-Singer in the smooth case, as a definition of a multi-signature. The topological manifolds, there are various approaches to how to generalize the topological manifolds. Let me mention there's an approach of Rothenberg and Weinberger, and then further generalization. That was the locally linear topological actions, and then Rosenberg and Weinberger, general topological actions. There's also another approach to topological actions, which is via the intersection chain complex, and that one works for singular varieties. And so this is even more generally, and that's due to myself and Janison and Weinberger. By the way, these approaches involve generalizing what the work of Telemann and Sullivan in the non-equivariant case, the equivariant situation. This approach, there's another approach which works even for many singular varieties, for example, complex varieties, and that approach is based upon using the intersection chain complex of the space. Take the intersection chain complex and think of a group acting on the intersection chain complex. Actually, think of the intersection chain complex as a sheaf, and if you handle this right, this sheaf, this equivariant sheaf, you can do it as a G equivariant sheaf, turns out to be an element of the homology theory, and so actually gives you an element which is, again, a generalization of the Atiyah-Singer class in an appropriate homology theory, KO homology theory, in the space X. At least if it convert to. So there is a general definition of the multi-signature, very, very general topological definition of the multi-signature, at least for varieties with even codimension. There's some real difficulties in varieties with odd codimension. But one can do this in very general setting. This, if I pursue down this road, it would take me to get further directions, this stuff, because this has this starts to tie in with singularity theory and algebraic geometry in ways that I don't have time to discuss, I think. But I'll say just that this is part of the background for the work of, in turn, of Brasselet, Yokura, Brasselet, Scheuermann, how do you spell Scheuermann? And Yokura on defining characteristic classes of a very general kind for complex singular varieties. Relatively recent work of theirs, and that work in turn has been used in algebraic geometric settings by myself, Maxime, and Shannon to define and study and compute very general characteristic classes of algebraic varieties. Even more general. And also the formulas for how they relate to singularities and maps. And formulate relating all these invariants to singularities and maps. So an enormous number of restriction on the complex singularities of a map given by these formulas. In fact, many parameter versions of restrictions on singularities of algebraic maps, which I won't have time to discuss here. It would take me in the direction of your other topic, and I just don't have time to do that now. But anyway, that's ongoing work, and there's also some further work of these same authors together with Lidgover on computing some of the relationships of this and its relationship to monodroming in algebraic geometry, which I also want to get into. Okay. All right, so those are some directions, but I have other directions that go back to Santiago that I want to emphasize. So I want to go all the way back now to Santiago again and talk about a quite different direction of Santiago's work. So I'd like to spend a few moments on something I found very inspirational, actually. Well, actually, so I'm going to talk about Santiago and low codimension and some maps. Santiago, starting with Santiago, I want to discuss submanifolds of low codimension. One of the things I learned from Santiago's book was the important distinction between submanifolds and characteristic submanifolds. So Santiago had studied, you see, he was looking at homotopy RPNs. Here's sort of a fake RPN, going back to the beginning. And Santiago was looking at the question also of, well, what can you say about sub-RPN sitting in here? Can you find, say, a fake RPK sitting in here? For which K can you do that? When can you do that? When can you find a natural, put it another way, the language of involutions, you're asking, suppose that you have a Z2 action on a big sphere, can you find some kind of a sub-equatorial sphere which is preserved by the group action, right? That's really this question. And Santiago emphasized the importance of distinguishing between finding general submanifolds, embedded submanifolds, embedded ones, such manifolds, and a particular class of embedded ones, which he called characteristic, which were the inverse images. These were the ones which were the inverse images of the standard one. These were inverse images of the standard one when we compared it to RPN. In other words, these were ones which were homotopically embedded in the standard way in some sense. These are embedded in some homotopic sense, standardly. And Santiago already observed that in small codimension, but not in high codimension, these two notions are the same. That in codimension 1 and 2, these coincide. These notions coincide. That's because there isn't enough room to construct an exotic homotopy situation in that codimension. But in higher codimension, these things do not always coincide. In fact, there's a theorem of Browder, beautiful theorem of Browder, Heftiger, famous theorem of Browder, Heftiger, Sullivan, left out Casson. Browder, Casson, Heftiger, Sullivan, Wall, different people had different pieces. Maybe Cornell also had a piece there. Which says the following, that if you here, let me put it this way, simply. Suppose I had an embedding, let's say, topological PL embedding. And suppose I had a homotop equivalent manifold. And suppose I had a homotop equivalence. Then the theorem says that the composed map, it can be moved to embedding. So this says that, in particular, what this theorem says that the problem of embedding one manifold in another in the topological PL category, provided that K is greater than or equal to 3, K is greater than 2, is you can always do it. You can always embed if you can embed a homotop equivalent manifold. This has, by the way, an odd consequence. If you remember your elementary theory of characteristic classes when you first learned it, one of the first things you learn about characteristic classes and the utility in geometry topology is that you can use characteristic classes to show non-embedding theorems. For example, some real projective space doesn't embed in another real projective space, and so on, in a sphere, and so on. It's one of the first things you learn about characteristic classes. At first glance, it seems to be contradicted here because the tangent problems of M and M prime can differ a great deal, and yet, and usually that's what they're using to show that you can't embed. But this thing tells you that you can embed despite that. So that seems a little bit odd. The reason you can do that is because in the PL in the smooth category, which you're more used to perhaps in elementary considerations, there's you know that a low-dimensional bundle cannot have high-dimensional characteristic classes, and that's why you're able to use characteristic classes to show non-embedding theorems. But in the topological PL setting, actually bundles can have surprisingly high characteristic classes. And so there isn't the kind of obstruction that you expect for this kind of embedding theorem. Anyway, applying this to RPN, Santiago was able to show many differences in phenomena between the embedded and the characteristics of manifolds, applying this result. Let me mention here some subsequent developments along this line. There's many stories I could go into here. So one is, there's a theorem of myself and Shannon, which says that this theorem is also true for K equals 2 most of the time, provided you're talking about M simply connected or R-dimensional. And if you allow yourself, and if you interpret the word PL embedding. Now, PL embedding, you see, correlation 2 can be of two different kinds. It can be either, it can have normal, you can have an embedding which is actually PL and actually an embedding, but can have normal singularities because it's embedded that way. So this theorem is still true in the PL category if you interpret and allowing normal PL singularities. You actually get PL maps to PL embedding, but they have the kind of normal singularities that arise, for example, in algebraic geometry quite frequently. So out of this, one can produce examples of very interesting embeddings in projective spaces beyond the examples that were studied by Santiago. I won't have time to go into that further. Let me mention also a recent result, equivariant result, which is related to this theorem, this Brown Wolf theorem, which is a theorem on the following problem. So I'm going to, let me hold off on that theorem because I'm thinking a little bit later. But let me just say, I won't have time to develop the theme of manifolds of small, but let me just say, the manifolds of small codimension, there's been a lot of interest recently in this, a renewal of interest in manifolds of codimension 1, and a lot of study of them. It turns out that there are sort of three cases to think about the manifold of small codimensions. There's the kind of case that Brown and Lipsig and Santiago thought about, which is the case when you have a manifold like codimension 1 with non-trivial orientation issue. And then there's other cases which are, in the oriental case, there's a case where the manifold doesn't split things into two, which is like, for example, in the situation studied by Brouwer for Pi1Z and Fallon Chang in general. When a manifold is cut in one, And then there's a yet more elaborate version of this case when there's more fundamental from on the outside, which was done by myself. And then there's also the case of manifolds decomposed into two pieces, which is, so this case was done by Browder with simply connected case, and various people were culminating, I guess, in my results on instructions to decomposition, yield groups and instructions to decomposition. Instructions to decomposition. Anyway, there are various people investigating now how to bring all these different points of view together, which I won't discuss them, but it's an area of current research which is based in part on these early probabilistic and considerations, the examples that Santiago developed to show that these things actually occur frequently, and so on. So I just pointing out that this is another theme that is a current one going on, actually. I want to say something about co-dimension 2 in Santiago, a little bit more. Because Santiago pointed out his book had some paradoxes that confused me a lot when I first read it. And I spent a lot of time in the 80s thinking about those paradoxes. Let me tell you what they were and why I found them so inspirational. Santiago pointed out that if you take, for example, an involution on RPN, and suppose you ask, not if it can be suspended once, but you ask, can you find an equivariant thing in dimensions 2 lower? Can you find an RPN minus 2 sitting in it? Can you find something with co-dimension 2 sitting in it? Now, it turned out, now of course, the study of co-dimension 2 submanifold begins with knot theory, right? Knot theory is the poor example of studying manifolds. Knot theory, we study a sphere of dimension n-2 embedded in a sphere. That's the core of what knot theory is about. And this was really the only example of co-dimension 2 phenomena that had been studied systematically, classically. Of course, that's a subject that flourished enormously in many ways and so on. I can probably survey that. But there had been no systematic attempt to go beyond the case of spheres and spheres to what happens for more general manifolds. And Santiago's work gave us some of the first interesting examples of phenomena that occur for manifolds beyond the sphere, actually, of this. And Santiago gave examples. There were examples. Santiago gave examples where an RPN contained an RPN plus an RPN minus 2. But only a knotted one. Only knotted. By an RPN, I mean a fake RPN, of course. Only knotted one. So that meant that you had examples where something could be embedded in something, but only at the cost of making the complement kind of complicated. So that was a strange phenomenon. That was the first time we saw that kind of phenomenon. And of course, somehow this was a phenomenon related to what one saw in knot theory, but one didn't really understand the relationship. Let me mention a couple of puzzles that I saw in paradoxes that I saw in the work of Santiago in this regard. One is that, so some paradoxes, and I'll just say a word or two about that puzzle us and not be alone, which is one puzzle was the following, that in studying these kind of phenomena and examples that Santiago gave, there was a dichotomy in phenomena. There was a dichotomy between even and odd dimensions. Even and odd dimensional phenomena. So different phenomena seem to come up. Now, of course, if you look at simply connected manifold theory, you can say, well, there's a dichotomy there also, because if you look at simply connected manifolds, there's a non-trivial surge obstruction like the signature in even dimensions. Nothing happens in odd dimensions. But that dichotomy disappears once you go over to the general non-simply connected case, and you realize that this is, so to speak, an accident of the trivial group. And in a more general setting, you can put yourself in a homology framework, there isn't that dichotomy between odd and even dimensions, no systematic dichotomy that way. On the other hand, in these codimension 2 problems, when one looked at the examples in Santiago's book, one noticed some more systematic dichotomies occurred between odd and even dimensions, and one wondered what they came from. Now, there was some other evidence of the dichotomy, because one also had the calculations of Crever and Jerry Levine on knot cobordism. So that was back in the context of knot theory, and there was a divergence between odd and even dimensions. In one dimension, they got huge groups. In another dimension, they got the zero group. But at first glance, one would think that that was the same dichotomy that you already saw in simply connected surgery between odd and even dimensions. So one wasn't clear on what role this dichotomy. There seemed to be some larger dichotomy, and one really saw that in the first examples of that phenomenon in some examples of Santiago. There also was a dichotomy between existence and uniqueness. Now, this is puzzling because in topology, the usual principle is that existence and uniqueness are the suspensions of each other. If you can prove an existence theorem, then by passing the sum across an interval, you can prove a uniqueness theorem. This is a principle in homotopy theory, in geometric topology, all over the place. So you don't usually see a divergence between existence and uniqueness theorems. So that was another dichotomy. And at the very beginning, when one thought about these things, one was even confused about whether these were two different dichotomies or the same dichotomy coming up. It took some time in the course of the 80s to sort this out. Let me tell you how I view this now, how I came to view this through work with Shannon in part, thinking about those and Santiago's and further examples, which is that the paradoxes in codimension 2 of this kind, so the dichotomy between even and odd dimensions turned out, I think, to be a good deal of it explained by the following. You see, when you're looking at a codimension 2 situation, you're always, suppose here I have a manifold W, and then I have a submanifold here, codimension 2. So you have to live with the fact that the fundamental group of the outside here is not the same as the fundamental group of the whole manifold. In this case, the fundamental group W minus M is the fundamental group of W. This is onto, this is surjective, but not injective in general. Just like the knot theory is already not injective. And that was occurring in the examples that Santiago was thinking about and so on. Now, Santiago pointed out that one would get interesting examples of phenomena by allowing the complement to have a more complicated homotopy theory, reflecting the fact that the homotopy theory was a module of this fundamental rather than that fundamental in that instance. If you take that point of view systematically, as Jules and I did, you'll then develop a homology surgery theory where you do surgery theory over this fundamental group, but try to construct things which have the right homotopy type over this fundamental group. So you're led to a kind of homology surgery where you have two fundamental groups floating around. One, the fundamental group which you're actually doing the construction. The other, the fundamental group, this is for the constructions, and this is where you kind of evaluate the result to see what homotopy type you have. And the reason you only care about this weaker fundamental group, the smaller fundamental group, is because in the end you're going to assemble the whole thing together, the whole manifold, and when you assemble that, you get back, for example, in Santiago's case, on RPN. You lose the complicated homotopy type that you have on the outside. Now, if you develop this kind of homology surgery systematically, it turns out that there's a radical dichotomy, unlike usual surgery, between odd and even dimensions in general. Because what happens is that there's a natural comparison map between the relevant gamma group, which is the homology surgery group, and the L group of the target, prime of W. And what happens is that this map turns out to be onto in even dimensions, but this is a huge group of quadratic forms, and this is in even dimensions. And in odd dimensions, it turns out to be injective rather than surjective, so it turns out to be a very small group. So there's a radical dichotomy between even and odd dimensions that occurs in the first place because homology surgery diverges radically. If you like, it's because it's very easy to lift quadratic forms. If I have a quadratic form in a quotient ring, it's very easy to lift the quadratic form to a bigger ring. It may not satisfy you the modularity of the big ring, but it's very easy to lift. On the other hand, if you take automorphisms of a ring, it's very hard to lift automorphisms of a ring. And that leads to a huge dichotomy between odd and even dimensions. So that was one dichotomy that grew, understanding that, grew partially out of thinking about Santiago's examples. And in other words, the dichotomy between existence and uniqueness, which I'll just say has to do with the fact that when you look at existence questions, you're studying closed manifolds. And when you're studying closed manifolds for these kinds of problems, you're looking at an element in a very big group, one of these gamma groups, either existence or uniqueness. But when you look at existence, you look at the image of closed manifolds in one theory. And closed manifolds are a very small thing. In sort of the Borders theory of closed manifolds that comes in is very small. So even though you're looking at very big groups for the existence questions, you get enormous limitation because of the fact that you're coming from closed manifolds. On the other hand, for the uniqueness question, you're looking at coordinates of things, and you don't have the same kind of coordinate theory, and so that turns out to be unlimited. And so for the existence, the dichotomy between existence and uniqueness, it turns out to be because existence is the image of a small coordinate theories. And uniqueness is not. This is large. And that's related to the largest that you see in optical coordinate theory, for example, and in the examples that occur in Santiago and so on. I won't develop that, but that's those two dichotomies and sorting out. I spent a lot of time thinking about the relationship between these two. Rich Anderson thinking about the relationship between these two dichotomies in Santiago, and realizing that they were, in some sense, two different phenomena, which needs to be sorted out. So I've got questions. Maybe I'm supposed to stop around now. So now I'm supposed to stop, I think. So I have various other strands, but those will be in, I mean, I could go, I actually feel, by the way, I could give a great course just on things that I learned from Santiago. And that would also be a survey course if it was only 1 year, actually. But I think his work and his influence goes to the present, and it's just a continuing source of not just inspiration, but a delight. If you go back and look at his book, it's just, it's just like candy. It's just so much fun to look at. So I want to express my and the community's gratitude for these wonderful contributions.
Are there any questions or comments? No, let's thank Professor Cappell for a beautiful talk. For one announcement, Professor Sylvain, he and his wife Moira are very sadly gone, and so we meet at next conference, which will be at 12:30. And if you want coffee, the best way to do it is to get into the students' cafeteria. The students are very good coffee makers. You just go out of the building. You will see people standing there having coffee, and obviously that's the best thing you take. There are cappuccinos, donuts. Highly recommended.
I mean, in my younger days,